This is a schematic diagram of the ripple tank that we use to make these pictures. The tank here is simply a wooden frame in which a plate of glass is mounted. With the glass carefully leveled, the tank is filled with water to about 2 centimeters depth. Light is projected from below by way of the mirror through the glass and water. We see the light focused onto the screen by the water waves, giving a pattern on the screen the same as the water wave pattern in the tank. A single drop of water serves as a point disturbance. The wave travels with equal speeds in all directions, keeping the pattern circular, and the direction of travel is perpendicular to the wavefront. We can create a straight wave by sharply rolling a long straight dowel in the water. Again, note the direction of propagation is perpendicular to the wavefront. It is difficult to make a single sharp, clean wave. You see secondary or minor disturbances which follow along with the principal wave, but they in no way will affect what we are looking at. A straight wave runs into a straight barrier and reflects. At an incident angle of 0 degrees, the reflected angle is also 0. Here, where the wavefront meets the barrier at 35 degrees, the angle of reflection is also 35 degrees. And at 45 degrees, again, the angle of reflection equals the angle of incidence. Indeed, for all positions of the barrier, the angle that the reflected wave makes with the barrier always equals the angle of incidence. Light, when it reflects from a mirror, shows this same behavior. So does sound when it reflects from a smooth barrier. If we consider each small segment of the circular wavefront, here too we find the angle of reflection is equal to the angle of incidence. This time follow the reflection along the upper half of the barrier. There. The reflected wave seems to come from an origin on the other side of the barrier, at a distance behind the barrier which is equal to the distance of the point source in front. This is called the virtual source of the wave. The circular wave reaches the barrier everywhere at the same instant and reflects back to where it came from. Each segment of the circular wave is incident on the barrier at an angle of 0 degrees and is reflected at 0 degrees. Here we get an artistic yet nondescript effect. As the point source moves along the principal axis toward one of the foci, the pattern becomes better organized. And finally, when the wave is generated at one focus of the ellipse, all portions of the wavefront reflect from the ellipse and arrive simultaneously at the other focus. At a certain point along this axis, the circular wave is reflected as a straight wave. This point is the focus of the parabola. For example, in a searchlight, the lamp is placed in the focus of a parabolic reflector. Compare these reflections from this barrier to those you just saw from the parabolic barrier. Right here, the central portion of the reflected wave is straight, but then only for a short time. Always part of the wavefront has a curved shape. This phenomenon is usually called spherical aberration. The reflection from this circular barrier is never the consistent straight wave which can be obtained from a parabola. Let's take a look again at what the parabolic barrier will do. The reflection is a perfectly straight wave. The straight wave appears to converge on the focus of this parabola, but it happens too quickly to see very clearly. So, in rapid succession, we repeat the straight wave, giving rise to a short wave train. Now it is much easier to see the waves converge on the focal point of the parabola. This barrier could be a radar reflector detecting microwaves, or the parabolic mirror of a large optical telescope. If you were to select a point anywhere on this wave pattern, you would find 17 wavefronts passing that point every second. This is a frequency of 17 cycles per second. Remember, we're seeing this at half speed, so here you really could only count half of 17. Now the frequency has been lowered to 12 cycles per second, and the wavelength is larger. If you observe these waves through a rotating slotted disc, a stroboscope, you can apparently stop the motion of the waves, and you can measure the distance between successive crests, finding the wavelength that's being used. This periodic straight wave has a frequency of 6 cycles per second. And now 12 cycles per second. A transparent plate has been placed in the lower right of the tank so that the water is shallower there than in the rest of the tank. The wave fronts are incident at an angle of 0 degrees on the boundary between the deep and shallow water, and they slow down when they cross that boundary. The velocity of the waves in the shallow water is less than that of the incident waves in the deep water, and the wavelength in the shallow water is shorter than in the deep water, while the frequency remains unchanged. Now the wavefront crosses the boundary at an angle other than 0 degrees, and here too the wavelength and velocity are less in the shallow area. But notice that the change of velocity of the wavefront as it crosses the boundary at an angle results in a change of direction of the wavefront. This phenomenon is what we call refraction. You can even see the waves partially reflected at the boundary and moving up out of the top of the picture. If we increase the angle at which the incident wavefront hits the boundary, the wavefront is bent more. It is refracted more than before. A beam of light passing into a block of glass refracts in the same way. You remember Snell's law describes this phenomenon precisely. You see a black marker placed on the screen, parallel to the wavefronts of the refracted beam. Now the frequency is increasing so that the wavelength is shorter. With the incident angle the same, the wave is refracted less. The refracted wavefront is no longer parallel to the marker. The angle of refraction is different at different frequencies. We see a similar phenomenon when white light is refracted by a prism, producing a rainbow spectrum. The lens-shaped area has an aperture of 10 to 15 wavelengths. Note the concentration of waves, a focusing effect, near the lens. Now the wavelength is decreasing, and the focal region moves farther from the lens. With water waves, the longer wavelengths are refracted more than the short ones. This effect is just the opposite in light, where the shorter wavelength of visible light, that is, blue light, is refracted more than red light. The dispersion of light waves by a lens is called chromatic aberration. Observe the waves just before they hit the lens. They are straight. As they cross the first boundary of the lens, they become slightly concave as you look at it from the right. Then as they cross the second boundary of the lens, they become even more concave. In this instance, the waves move from shallow to deep water, the reverse of what you saw before. This time the area in the lower right of the tank is deeper than in the rest of the tank. The wave fronts are incident at an angle of 0 degrees on the boundary between the shallow and deep water, and both the velocity of the waves and their wavelength increase when they cross that boundary, just like light coming out of water or glass into air. Here, where the wavefront crosses the boundary at an angle, again the wavefront is bent. Only this time the wavefront is bent in the opposite direction from before, since now the refracted waves travel faster than the incident waves. As the incident wavefront hits the boundary at a larger angle, the wavefront is refracted more. And the angle of incidence between the wavefronts and the boundary can be increased to such a value that the refracted waves Just skim along parallel to the edge of the boundary. If the angle between the wave fronts and the boundary is increased beyond this critical angle, there is no longer any refraction. No wave is transmitted at all. The entire wave is totally reflected, and the angle of reflection from the boundary is equal to the angle of incidence.